Here is a graph of f and a graph of g. Express g in terms of f using function notation. So function f is the graph to the right, and function g is the graph to the left. They have pointed out these points at the peak, and we can see that the y value is 1 for both graphs, but we can see that we have gone from 0 as x on f of x, and we've shifted left 3 spots to -3 on the graph of g of x. So we would say that g of x equals f of x plus 3. Because if we add inside the parentheses, we are shifting left that many units. Tyler leaves his house at 7 a.m. to go to school. He walks for 20 minutes until he reaches his school, 1 mile from his house. The function d gives the distance d of t in miles of Tyler from his house t minutes after 7 a.m. Explain what d of 5 equals 0.25 means in this context. So in this case, 5 is t, and t is minutes after 7 a.m. The 0.25 represents the distance in miles of Tyler from his house. So that means Tyler is 0.25 miles from home at 7:05 a.m. On snowy days, Tyler's school has a 2-hour delayed start time, which is 120 minutes. The function s gives Tyler's distance in miles from home t minutes after 7 a.m. with a 120-minute delayed start time. If d of 5 equals 0.25, then what is the corresponding point on the function s? Well, if we originally had d of 5, but now we have a 120-minute delay, then that means the corresponding time would be s of 125, and now that would still equal 0.25. We've just added in the 120-minute delayed start time. Write an expression for s in terms of d. Well, s was 125 and d was 5. So if I'm writing an expression for s, then s of t equals d of t minus 120, because I would need to take this 125 and subtract 120 to get the original d of 5. A new function n is defined as n of t equals d of t plus 60. Explain what this means in terms of Tyler's distance from school. So now we're talking about an equation where we're adding 60 inside the parentheses. Now, a 120-minute delay meant we were subtracting 120 minutes. So if we're adding 60, that means Tyler left to start walking 60 minutes earlier. So this would mean Tyler's distance when starting 60 minutes earlier. And if you think about what we've done with graphs up to this point, when we see minus inside parentheses, we're shifting that graph to the right. So that's a later start. And when we've seen addition inside the parentheses, we're shifting that graph left. So this would be starting 60 minutes earlier. The dashed function is the graph of f, and the solid function is the graph of g. Express g in terms of f. So if you look at the dashed graph in relation to the solid graph, you can see that what has happened is that our graph has been reflected across the y-axis. So what I want is the opposite of my x-coordinates. And if you think about how we would symbolize opposite, we symbolize that with a negative. So if I want to express g of x in terms of f of x, but I want the opposite, then I want my negative inside the parentheses with the x. This would give me the opposite of whatever I had. So for comparison, this point on f of x is negative 2. But if I take negative 2, I get positive 2. This point right here is x equals negative 1. But if I take the opposite of that, or negative 1, I get positive 1. So anytime we put the negative in front of the x inside the parentheses, this will reflect across the y-axis. On this one, we're going to use technology. I am going to show you the Desmos.com calculator. This is a good free online graphing calculator that you should get used to because it is built into a lot of the standardized tests now, like the SAT and PSAT. Here are the data for the population F in thousands of a city D decades after 1960, along with the graph of the function given by f of d equals 25 times 1.19 to the power of d. So the individual points are the data for the population. The solid line is the graph of function f. Elena thinks that shifting the graph of f up by 50 will match the data. Han thinks that shifting the graph of f up by 60 and then right by 1 will match the data. What functions define Elena's and Han's graphs? So first off, Elena wants to shift up by 50. So Elena's would be 20, or I'm sorry. Elena's would be 50 plus 25 times 1.19 to the power of d. All she is doing is shifting it up. So when we shift up, we add 50 outside of the original function. Then Han he wants to shift up by 60, but also wants to shift right by 1. So if you remember, when we're shifting right by 1, we need to subtract 1 from the input. So this first equation would represent Elena. The second one would represent Han. And now they want us to use graphing technology to graph Elena's and Han's proposed functions along with f. So on this graph, I have already narrowed the window down to the measurements that we have on the graph on the worksheet. You can see that we go from 0 to 150 on the y-axis, and we're counted out by 25s. And then you can see that we go from 0 to 6 on the x-axis, counted out by 1s. Now when we look, this first equation here is Elena's. And it's going to start at 75, and then it's going to end right up here around 120-ish when it gets to 6. So Elena's starts right around here, and it hits right around here, and we've got that steady kind of same incline as this solid line down here. We're just shifting it up. And now we'll look at Hans. And Hans is this green line right here. We can see that it goes up and starts around 80-ish and then still meets right around in that same location. So Hans is going to start a little bit higher. It's still going to end right around the same location. So we can kind of draw it like this right here. So on mine, this red line on the bottom is representing Elena, and then the top line here is representing Han. And now for part 3, they want to know which graph do you think fits the data better and explain your reasoning. And if you look, they both seem to be about the same distance away from these top 3 points over here on the end at 4, 5, and 6. But if we look down here at the beginning, the bottom line is much closer to the first point. It actually seems to go right through the second point, and then seems to be fairly close to 2 and 3, which so does Han's line as well. But it does appear that Elena's line fits these first couple of points better than Han's. So Elena's graph seems to fit the data points better. And this is how you could solve a problem like this. When it comes to using the Desmos calculator, it's just desmos.com/calculator. You can click in any of these boxes. There's a keyboard down here in the bottom left, and you can type your equations in using this. You have x and y. You have an a to the power of b button, which allows you to type in exponents such as x or x minus 1. You just have to use the parentheses if you're going to do x minus 1 as a power. You have your parentheses that you can use, and then a normal calculator. And it will actually change the colors of the lines so that you can tell which one is which. And then this allows you to have the technology graph it for you, and then you can go on the worksheet, draw it as close as you can, and then be able to evaluate your answers. Here is a graph of y equals f of x plus 2 minus 1 for a function f. Sketch the graph of y equals f of x. So what they're saying is that the graph they have drawn, if this is plus 2, that means this graph has been shifted left 2 units from the original. And if it has minus 1 outside of the parentheses, that means it has been shifted down 1 from the original graph. So we need to find some points here. This point at -7 would need to be shifted to the right 2 and up 1, and we could put a point. This point at -5 would need to go right 2 and up 1. This point at -3 would need to go right 2 and up 1. This point at -1 would need to go right 2 and up 1. And this would need to continue. We need to go right 2, up 1. This point would need to go right 2, up 1. This point here would need to go right 2, up 1. And now we could draw this graph. And we could say that this was f of x if the graph that they originally drew was f of x plus 2 minus 1. Now you could see that if the red graph we drew was the original, then the one they drew has been shifted left by 2 and down by 1. The thermostat in an apartment is set to 75 degrees Fahrenheit while the owner is awake and to 60 degrees Fahrenheit while the owner is sleeping. The function W gives the temperature W of x in degrees Fahrenheit in the apartment x hours after midnight. When it is hot outside, the owner changes the settings to be exactly 10 degrees warmer than W to save energy. The function h gives the temperature h of x in degrees Fahrenheit x hours after midnight when it is hot outside. Number 1. If W of 6.5 equals 75, then what is the corresponding point on h? Use function notation to describe the point on h. So here we're going to be talking about function h. So it is the temperature that is going to change, not the number of hours after midnight. So we would still have h of 6.5. But the temperature is now going to be set 10 degrees warmer. So if originally that temperature was 75, that is now going to be 85. So the corresponding point would be h of 6.5 equals 85. Number 2. If W of 2 equals 60, then what is the corresponding point on h? Use function notation to describe the point on h. Again, we're talking about function h, and the time is not going to change. It's the temperature that's going to change. If the temperature here is 60 and we're going to increase it 10 degrees, h of 2 equals 70. And number 3, write an expression for h in terms of w. So as we saw, we would have h of x, and in relation to w of x, that's going to be w of x plus 10. It's the output value that is being increased by 10, not the input value. The table gives some values of functions f and g. Which of these equations could be true for all values of x? Now, a quick way we could do this is to do some quick sketches. All right. So we'll do f of x in red, and that says if we go to -2, then our y value was 4. At -1, our y value was 2. At 0, our y value was 1. At 1, the y value was 1/2. And at 2, the y value was 1/4. So we have a line that is going down and getting closer and closer to the x-axis. Now we'll do g of x in blue so we can tell the difference. This time, when x was -2, our value was 1/4. At -1, our value was 1/2. At 0, our value was 1 again. At 1, our value was 2. And at 2, our value was 4. And now we can see the graph of g of x. So, if we go through and look at what the equations are telling us, A has the negative outside of the parentheses. So this would turn our y values negative. This is what it looks like when we reflect across the x-axis. In other words, flip it upside down. We can see that that's not what happened in our graph. So now we can look at B. We have the negative inside the parentheses with the x. This is what it looks like when we reflect across the y-axis. In other words, flip it over from left to right. And that does appear to be what happened. If I take this red graph and I spin it around the y-axis, I end up with that blue graph. So B appears to be the correct answer. Just to check, C, f of x equals negative g of negative x. This means reflect across both the x and y axis, which means we would flip it upside down and flip it around to the other side of the y-axis. And that's not what happened here. And then D says f of x equals g of x. The graphs would be the exact same. So looking at this, we can tell that what happened was B, it was reflected across the y-axis. Here's the graph of a function f. Number 1, on the same axis, sketch a graph of f reflected over the y-axis and then translate it 3 units up. So we need to find some points here. This point seems to cross at about 2.5. If I was going to translate this across the y-axis, I would need to go to -2.5. But I also need to translate it up 3 units. So now I'm going to move it up to where I would say 3 is. Another good point would be the y-intercept. This looks to be at 0, 3. I'm going to move it up 3 to the origin. And now what I would have, if I could find one more point, let's say this point appears to be about -2, -5. Reflected across the y-axis, would mean take it to positive 2, negative 5, and then translate it up 3 would put a point right about here. So now what I have, we're going to see the line come up, and then it's coming down. So I found a few points where I thought I could identify where they were. I translated them across the y-axis, so I made them the opposite of what they were, and then I translated it up 3 units. Number 2, write an equation in terms of f for a function g that has the graph we drew. So now we're going to have g of x. If we translate it across the y-axis, then that's going to be f of negative x inside parentheses, because the negative with the x inside parentheses gives us the opposite x values, or translates it across the y-axis. But then we're going to add 3 outside of the parentheses, because that tells us to shift it up 3 units. A ball is hit in the air. Its height, h, in feet, t seconds after it is hit is modeled by the equation h equals 4 plus 50t minus 32t squared. Which equation models the height of a ball following the same path, but it is hit 2 seconds after the first ball? So we need to look at what it's telling us. All right. We know the same path 2 seconds after the first ball. Now, t in time is the x-axis. So if we are going to have the same path be 2 seconds later, we are shifting this 2 units to the right. When we shift 2 units to the right, we subtract 2 from the input. And that is what we get in choice D. The others are not correct, because in this one we added 2 to the output. So this shifts up 2 units. B subtracted 2, so that shifts down 2 units. And this one added 2 to the input, which shifts left 2 units. As we said, this new path is coming 2 seconds after the first path, which means it's shifted right, and that's what the bottom one shows. It shifts right 2 units. Here is a graph of function f and a graph of function g. Express g in terms of f using function notation. So the graph on the left is f, and the graph on the right is g. If you notice, they have the same shape, so they have not been reflected. So they pointed out this point at the peak at 0, 1, and that same point at the peak at 0, -2. So the x value didn't change. It's 0 on F and it's 0 on G. But we went from 1 to -2. So what they did was they shifted this down 3 units. So if we want to write g of x in terms of f of x, we subtract 3 outside the parentheses, and that means to shift it down 3 units. This is our last practice problem for lessons 3 and 4. Describe a transformation of the line that contains the two labeled points. So we have talked about a couple of different ways to transform a graph. We have talked about shifting up. Well, if we shift up, this point would need to go from -2 to 1, so that would be 3. This point would need to go up from -0.5 to 4. That's a shift up of 4.5. So we would actually have to tilt this line in order to get it to fit, and we have not covered how to tilt it. We also couldn't just shift it sideways because they have different slopes. So we can't shift up, we can't shift left because we have this tilting factor to it. So what we could do is a new method. What we can do is take a line that goes through both of these points. If we extend this line down and up, we could see that the original line, if we kept drawing it out, would eventually cross paths at this point right here. And then we could say there's an imaginary line going down the center, and we would need to reflect across this dashed line that I created. So in this problem, they just want to make sure you understand that in order to do a shift up, you would have to be able to shift the whole graph up the same amount to have it fit. If you can't do that, you can't do a shift up. They also want to make sure you understand that if you tried to shift left, you're having to shift the entire line left the same amount. If it doesn't fit, you can't just do a simple shift left. So whether you're shifting up or left, or whether you're reflecting across the y-axis or the x-axis, in order to use those manipulations, it has to fit exactly. And in this case, none of those transformations that we covered would work. So you would have to do something like this, where you draw a new line, you find where these two lines cross, and then you say that you reflect across that point in order to get the new one. And that's as far as we're going to take it right now. We're not going to try and figure out what any of the equations would be for that. We just want to make sure you understand how to properly shift up or down, shift left or right, or reflect across either of the axes. So these are all the practice problems for lessons 3 and 4. If you have any questions, please use class time to get clarification before we start in on lessons 5 and 6.